Hello and welcome to my quick presentation about the new features of Java 21. Due to its limited length, I won't be able to cover the non-final features in Java 21, and also I won't have time to go into all the details. So in case you're interested in more detail, feel free to reach out to me via my contact link and we can discuss more. My name's Marian Varga. I'm a freelance contractor specializing in integration, APIs, and microservices. And besides Java, I like the Kotlin language. Java 21 was released in September 2023, and even though in a few days there will be Java 22 released, we will be hearing about Java 21 for some time because it's an LTS, which means a long-term support version. The previous LTS versions were 17, 11, and 8. As to the features that are in Java 21, the bigger features that are separately specified are called JEPs. There are 15 of them in Java 21, and almost half of them are not final, which means they are in a preview or incubator state. If we take a look at the versions since the previous LTS version, in Java 20 and Java 19, there are almost no finally delivered JEPs. In Java 18, there are some final JEPs, but probably the most interesting one that I want to mention here is that UTF-8 is defined as the default encoding for conversion between strings and byte arrays, which fixes a lot of errors that were caused by the fact that the encoding wasn't explicitly specified and it was dependent on the environment of the operating system where the application was run. So as we can see that the non-LTS versions usually don't finalize the JEPs, and the delivery of the features is usually aligned to the LTS versions. But the non-final versions are important as well, not only to be prepared for the future, but also you can test your application with the new features and you can provide feedback. JCP is the organization that unites all the entities that contribute to the development of Java, and you too can be member of JCP. Even individuals can apply to become a member of JCP. I tried it and it works, and as a member of the JCP you can provide this feedback and you can influence the future of Java. Let's try to answer the question why we actually should upgrade to a new version of Java. Well, if we talk about security, one can argue that actually the reason why we use an LTS version is that there will be security patches for the version, but that doesn't mean that doesn't mean we're done with security. Our application also depends on frameworks and libraries, and if we take an example of Spring Boot 2, which is no longer supported, we have to switch to Spring Boot 3, and that has a requirement to have a minimum Java version 17. So in case we were on Java 11, we would have to upgrade even though there might be security patches for Java 11. Performance is also an important factor. If we are using an old version of Java, we are missing out on the opportunities to gain better performance for our applications, so we are wasting compute resources. And code readability is something that can greatly improve the time we spend in maintaining our applications and can decrease the number of errors. So be it you, your manager, or your customer who tries to delay upgrading Java, it's probably an idea where you should understand this is introducing a technical debt. That means if you are reluctant to upgrade today, that will probably mean you will come to the point where you need to upgrade either way, but the upgrade will be much more urgent, much more painful. So is it worth the problems? Now let's go to Java 21 features, and the first group of features is the language changes or syntax changes. If we compare it to the previous LTS Java 17, in Java 17, or actually from Java 16 already, we have a revolutionary change in the introduction of the record type. In case you don't know this type or you don't use it, look it up, because it's really can improve your code base a lot, and it also has impact on libraries and frameworks. Now in Java 21, a feature builds on the record type, and basically the record patterns is a deconstruction of a record type. That means we can use a pattern to describe the structure of our record, or it can even be a structure of record inside another record, and we can easily access its internal components without code that is hard to read. Now, pattern matching is a broader topic, and the part where it improves the syntax the most probably is the switch statement or switch expression. So Java is extending the ways how we can use the switch statement or switch expression. We can test for the type of the objects that coming to the switch expression, and we can immediately use a variable that is typed to the matching type. Also, with sealed classes and the switch expression, we get a check if all our possibilities mentioned in the switch cover all the possible cases. This is especially interesting for sealed classes or sealed interfaces. Now we can also pass null into switch without getting null pointer exception, and we can combine the test for type with an arbitrary Boolean expression. So basically we can replace most of the if-else sequences by much more readable switch statements or switch expressions. Let's move to changes to the built-in libraries of Java. Everybody uses collections, and the sequence collections JEP is about a cleanup in the collection types in Java with regards to those collections that define or preserve the order of the elements in the collection. Now we have new interfaces, sequenced collection and sequenced map, and with methods to access first and last elements uniformly across all the relevant collection types. And also we have a reversed method to get a reversed order of the collection. There's a new API called Key Encapsulation Mechanism. It is related to cryptography, and it basically abstracts class of cryptographic algorithms that will be quite important for the future. So if you want to be prepared for post-quantum cryptography, you should probably take a look at this new API, but we don't have time to go into more detail. Now we come to performance improvements in Java. One of them is the introduction of a new implementation of a garbage collector called Generational ZGC. This one is finally delivered in Java 21. Nevertheless, it is turned off by default, and you need a command line switch to turn it on. And to know if a particular garbage collector implementation is the one for you, you should probably first run some kind of a profiler and find out the characteristics of how your application uses memory allocation and how the objects are collected, what are the size and the lifetime of your objects. So in case you think that garbage collection might be causing performance problems in your application, you can also take a look at an Oracle page that is quite a nice introduction to choosing the right garbage collector implementation. But the feature that I want to talk most about is virtual threads. It's a feature that is much discussed in Java 21. Unfortunately, it's also a feature that is probably the hardest to explain. So I will try to use maybe a little bit oversimplification just to explain the basic ideas. I will call it garbage collector for threads. Let's take a look at a typical application running on a server that and handling some requests coming to the service. We can see we have an annotation for some framework that basically ensures that each request that we receive is processed in one thread. Now, what does executing a code in one thread mean to a programmer? Basically, it is a great thing because that means our code is executed in the exact order as it is written in our source code. So that makes reading, debugging, maintaining our code quite simple. Typically there might be multiple lines of code that manipulate the data locally, and then in between those sections of code with the local processing there are some that access another API, or maybe they access a database, or maybe they manipulate files. So some code that needs some input or output. And if we take a look at the runtime characteristics of such code, we discover that those multiple lines, many lines that do the local processing, actually run much smaller time, much shorter time comparing to those that invoke some external communication. And this ratio can be thousands up to a million. So here we have microseconds, and the external calls can take milliseconds to seconds. So statistically, this means such application under a load, if we take a snapshot of it, we will see that 99.9% of the threads will be blocked because they will be executing or basically waiting in such external calls. Now, this can create a problem because the traditional way of implementing threads in Java was that each Java thread was implemented using exactly one platform thread or thread provided by the operating system. The platform threads are an expensive resource. Each of them takes quite a lot of memory, and so there's a limited number of platform threads that an application can use. So if we use all the available platform threads, then we get to the situation that our service or our application cannot process more requests, even though actually the CPU doesn't have anything to do, because it's just waiting for input and output operations. So what do we do now? Of course, there are solutions to this problem, and one of them is reactive programming. With reactive programming, we change the structure of our code so that basically we first build something of a pipeline, and the actual execution of our code is not from top to bottom, but it's from bottom to top. And there are also some other problems, like if an exception is thrown, from the stack trace of the exception, it's not visible what steps exactly led to the exception. So it brings a lot of additional complexity that is not caused by our business domain, just the technical reasons. And of course, if there's a legacy application, rewriting the application to use reactive programming would be very hard, maybe even impossible, because we would have to rewrite all the layers of the application. If we start with reactive programming and then in some middle layer we use blocking code, then actually it doesn't bring the fruits that we expect. So how can we do this better? And Java helps us with various useful abstractions. One abstraction that all of us know from the first version of Java is the garbage collector. When we create a new object in Java, we don't get direct access to the memory that the object occupies, we get a so-called reference. And the advantage of this indirect approach is that the JVM has the power to detect the point when there are no references to an object, and at that point the memory can be automatically freed. So our application code doesn't have to pollute the business logic with low-level memory handling stuff. Now, the virtual threads are similar in the way that the only thing we need to do is to tell our framework that we had the annotation for here to use virtual threads instead of the platform threads. Now, when our handler method is executed with a virtual thread, while it's using the local processing, the CPU-based processing, there's no difference. But once we hit an input-output operation, due to the fact that we use a virtual thread and we use JVM internal libraries to do the I/O operations, in the implementation of those I/O operations, the JVM is able to detect that it's a virtual thread, and in that case, before blocking, it can move the state of the execution to the heap memory and use the platform thread from other work, so it doesn't have to wait. And once the I/O operation is finished, the JVM can take some free platform thread. It can be a different one from the one that we used before the I/O operation, and assign the virtual thread to that platform thread, while the application still sees the same virtual thread. So our assumption that our code is executed by one thread is still fulfilled. So we still can get the benefits of writing a simple sequential code. Now, there are also situations when we want to create threads explicitly in our application code, when we know that we want to do some things in parallel while handling just one request. It's already a little bit more complicated, and we have to think what kind of work we are going to parallelize. If the work that we want to parallelize involves a lot of I/O operations, so for example, if we want to invoke 5 different APIs in parallel and then somehow collect their results and create the result of our originating request, then of course it's a good idea to use virtual threads. And as we can see, comparing to the older code, we no longer use thread pools. Thread pools were used to actually limit the number of platform threads that we want to use, so that we don't go over the limit. But with virtual threads, we don't have such limit, because the virtual thread is a cheap resource that is like the objects in with garbage collector that can be created and then automatically garbage collected. The same applies to new virtual threads. we can create them as many as we want, and the JVM handles the internal stuff for us. Of course, if there's, on the other hand, if the work that we want to execute is mostly local and CPU intensive, then probably it's a good idea to stay with the old or existing platform threads, because the virtual threads, while they are good at reusing platform threads when they would be blocked, they cannot switch platform threads while doing CPU work without any blocking. So using platform threads has the advantage that operating system threads have the power of switching between threads even during CPU intensive work, and this way the distribution of the CPU among all the tasks that need the CPU is much more even and and it prevents starvation of some of the threads, basically. Basically, of course, virtual threads cannot add you more CPU power, right? And the same thing we have to consider regarding memory, because yes, we do save the memory that would be needed to create a lot of platform threads, but if the code that we are using in our virtual threads code allocates some memory on the heap, and we have to consider the fact that there can be hundreds of thousands or million virtual threads at the same time, so the amount of memory that we will consume can grow quite quickly, and we have to be prepared for it. So again, virtual threads cannot extend our RAM, of course. After talking about virtual threads, I also want to mention two JEPs that are in preview state, but they are strongly related to virtual threads. The first one is structured concurrency. This is a feature that brings order in concurrent code that explicitly creates multiple threads, as we've seen in the previous slide, in the way that no thread that we create gets loose or uncontrolled. Basically, when we create multiple threads to do some parallel work, we want to make sure that when the work ends, either successfully or with a failure, all of the threads created are terminated. This also applies to trees of threads. So if we create multiple threads and some of those threads again creates multiple threads, we want the whole tree to be terminated, so that there are no threads that we somehow forget about. Scoped values is another important feature that will in many cases replace the thread local type that is used to transfer some data on the background, so to say, under the assumption that all the related pieces of code run in the same thread, and we don't want to pass all the data via explicit function arguments or method arguments. With scoped values, we get again more order in this, because firstly, the scoped values are immutable. thread local is mutable, and that can bring a little bit of a chaos. And scoped values work the way that there's a function or a lambda that that defines the scope where the thread local values are available, and when this lambda returns or ends, the scoped value is automatically removed, so we don't have to do an explicit thread local remove. Okay, so that's it. Thank you for your attention, and again, if you want to know more about Java and Java 21, feel free to contact me and we can talk more.